These are the answers to homework 1B. Here are the definitions I'd like you to know. Now let's go to the questions. Number 1, at 1476 Kelvin, the equilibrium constant for the reaction CO plus 1/2 O2 in equilibrium with CO2 is given by Kc equals 2.50 times 10 to the 5th. A, determine numerical value of the equilibrium constant Kp for this reaction. If we're given a Kc value for a reaction, we want a Kp value. The relationship is Kp equals Kc multiplied by RT to the delta N, where delta N is moles of products minus moles of reactants that appear in the equilibrium constant expression. From our reaction, we have 1 mole of products, 1 mole of CO2, and we have 1.5 moles of reactants, 1 mole of CO, 1/2 mole of O2, so the delta N value turns out to be -1/2. I didn't include the units for the Kc in this problem, but if we know what the delta N value is, that tells us the exponent for the units. So a Kc is always the ratio of molarities, and so the units for this Kc would have to be molarity raised to the -1/2 power, or you could say moles to the 1/2 over liters to the 1/2 reciprocal. So liters to the 1/2, moles to the 1/2, another way to write that. So the relationship to calculate the Kp is this. We have our Kc value, 2.50 times 10 to the 5th. I'm going to write it as liters to the 1/2 over moles to the 1/2. And then in brackets, our RT value, 0.08206 liter atmospheres per mole Kelvin, multiplied by 1476 Kelvin, all raised to the -1/2 power. All the units are going to cancel out here except for the atmospheres, and the atmospheres are raised to the -1/2 power, so the final units will be atmospheres to the -1/2. And if you do the math correctly, it comes out to be 2.27 times 10 to the 4th atmospheres to the -1/2, a 3 significant figure value because the Kc was the factor with the least number of significant figures in the calculation. Part B, what would be the numerical value of the Kp for the reaction 2CO plus O2 is in equilibrium with 2CO2. This reaction in Part B is related to the reaction written in Part A. It's the same reaction except it's been multiplied by 2. So if you multiply a reaction by 2, that means you have to raise the original equilibrium constant to 2 as a power, or in other words, to the second power. So we calculated the Kp for the reaction in Part A as 2.27 times 10 to the 4th. We would now have to raise that to the second power to give us the Kp for the reaction written in Part B. So that would be 2.27, and I'm going to go back and use a guard digit that I had calculated from Part A, 2.272 times 10 to the 4th atmospheres to the -1/2. If we raise that to the second power, that's going to be the equilibrium constant for the reaction written in Part B, and that comes out 5.16 times 10 to the 8th, and the units turn out to be atmospheres to the -1 because I'm multiplying -1/2 by 2 to get the exponent for the units of atmospheres. Question number 2. When sulfur trioxide is produced from the combination of sulfur dioxide, or rather the combustion of sulfur dioxide at 1000 Kelvin, a sample of the equilibrium gas mixture shows 0.562 atmospheres of SO2, 0.101 atmospheres of O2, and 0.332 atmospheres of SO3. A, calculate the equilibrium constant Kp for the reaction 2SO3 in equilibrium with 2SO2 plus O2. So if we want the equilibrium constant for this reaction in terms of partial pressures, we're calculating a Kp, and we need to write the Kp expression. Products over reactants, products always on the right side. So on the right side is SO2 and O2, so it's the partial pressure of SO2 squared multiplied by the partial pressure of O2, then divided by the reactants, partial pressure of SO3 raised to the second power. In this case, they've told us all the equilibrium partial pressures of these 3 gases. We just have to plug them into the expression and multiply it out. These are all 3 significant figure numbers, so our Kp will come out to be 3 significant figures. And in terms of the units, we have atmospheres cubed on the top, atmospheres squared on the bottom. So the Kp's units will come out to be atmospheres to the first, and the numerical value turns out to be 0.289. B says determine the numerical value of the Kc for this reaction. So the Kc's and the Kp's are related through the expression Kp equals Kc multiplied by RT to the delta N. And in this particular problem, the delta N value comes out 1 because we have 3 moles of gaseous products and 2 moles of gaseous reactants. 3 minus 2 is 1. Solving the expression for the Kc will equal the Kp value divided by RT raised to the delta N. So the Kp value from part A, using a guard digit, 0.2894 atmospheres, divided by R times T raised to the first power. Atmospheres cancel out, kelvins cancel out, and the units wind up to be moles per liter, numerically to 3 significant figures, 3.53 times 10 to the minus third. You could write that 3.53 times 10 to the minus third molar if you want, but that would be the numerical value of the Kc. Part C, calculate the numerical value of the Kc for the reaction SO2 plus 1/2 O2 is in equilibrium with SO3. This reaction is related to the very top reaction of the slide with 2 corrections. First, the reaction is reversed. So if we've now reversed the reaction for C, that means the reaction for A's equilibrium constant, we need to take the reciprocal of that. So whenever you reverse a reaction, you always take the reciprocal of the original equilibrium constant. So when we reverse it, we'll take the reciprocal. The second thing is now the reaction in C is the same as the reaction in A, but it's been multiplied by 1/2. So if we multiply a reaction by 1/2, we have to raise the equilibrium constant to the 1/2 power. So in this case, we have 2 corrections we have to do to the Kc value for our original reaction. We've got to take the reciprocal of it, and then we've got to raise it to the 1/2 power. Now the Kc for the original reaction was calculated in part B. That's the 3.53 times 10 to the minus third moles per liter. So I'm going to take the 3.53 with a guard digit, so 3.527 times 10 to the minus third molar, take the reciprocal, which means raising it to the -1 power, raise it to the 1/2 power, so -1 times 1/2 is -1/2. So combining those, I'm going to take my value for my Kc and raise it to the -1/2 power, and that's going to give me the equilibrium constant, the Kc, for the newly written reaction in part C of 16.8 molar, and the units turn out to be molar to the -1/2 as our final answer. 3. Complete an initial change in equilibrium molarity table for each of the following. So if we have a reaction between A and B turning into C, and we're given 3.0 molar of A and 3.0 molar of B, if the reaction does not go to equilibrium, but does not go to completion, but reaches equilibrium, we don't know how much of the A and B react away, so we have to use variables of X. But in order to keep the stoichiometry in the reaction correct, we multiply the X by whatever the coefficient is in the balanced equation. So the A is going to be reacting away because we have A and B in the container, so they're going to react away to form C. So I'm going to subtract 1X of A, that's how much is going to react away. Stoichiometrically, you would have to react, therefore, 2X of B, so that's what's going to react away. We're forming the product, so we're going to create that. It's going to be plus 1X for the amount of C that's created. Adding up the columns will give you the equilibrium molarities, 3.0 minus X molar for A, 3.0 minus 2X molar for B, and X molar for C. For our second one, the reaction between D and E forming F, similarly, we're given molarities for D and E. They're in the container, but there is no product in the container, so the forward reaction has to be spontaneous. The D and the E are going to react away, so their changing moles are going to be negative, and we're going to be forming F, so its changing moles will be positive. Using X as the amount of chemical change multiplied by the coefficient in the balanced equation to make the stoichiometry work, we would react away 3X of D with 1X of E. We would form 2X of F. So the equilibrium molarities would be 4.5 minus 3X for D, 2.0 minus X for E, and 2X for F. Number 4, at 298 Kelvin, Kc equals 2.25 times 10 to the second for the reaction 2NO is in equilibrium with N2 plus O2. Part A, If a container is initially charged with 7.50 molar NO, what will be the equilibrium concentration of NO? So in problem number 4, we're given this reaction in which the equilibrium constant is 2.25 times 10 to the second, and that's a Kc, so it's the ratio of molarities. And they tell us we're starting with an initial molarity of NO of 7.50, and that's all it says, so you can assume there's no nitrogen and no oxygen in the container. Because there's only reactants present and no products, the forward reaction has to be spontaneous. Some of the NO will react away, and because it reaches equilibrium, it's not all going to react away. Some unknown amount X is going to react away, but stoichiometrically, it's going to be X multiplied by the coefficient in the balanced equation. So we're going to react away 2X molar of NO. You would have to form 1X molar of N and 1X molar of O. The equilibrium molarities will be 7.50 minus 2X, X, and X. These equilibrium molarities are related to the equilibrium constant because it's the ratio of the molarity of the products to the molarity of the reactants. If we write out the Kc expression, the equilibrium constant expression, it's going to be products over reactants, molarity of N2 times the molarity of O2 divided by the molarity of NO squared. When I say equilibrium constant expression, I mean this. We're just showing how the reactants and products equal the constant with their appropriate exponents. If you want to calculate the numerical value of the equilibrium constant, that would be the numerical value of Kc, which they've given in the problem, 2.25 times 10 to the second, or 225. So we know the value for the Kc, and it's going to be related to the equilibrium pressures of the three different gases. So the 225 is going to equal X times X divided by 7.50 minus 2X quantity squared. This is an easier algebraic problem to deal with because the right side of the equation is a perfect square, which means all we have to do is take the square root of both sides of the equation, and we'll have a problem in which X is only raised to the first power, and it'll be easy to solve. So square rooting both sides, it turns out the left side happened to be a perfect square as well, but keeping three significant figures, it comes out to be 15.0. And the square root of the right side is X over 7.50 minus 2X. I'll allow you to do the algebra for this. If you can do it correctly, you should be able to calculate that X equals 3.63. So if that's your value for X, and the question asks, what's the equilibrium molarity of the nitrogen monoxide? What is the nitrogen monoxide concentration at equilibrium? Look under NO in your ICE table. On the equilibrium line, it says it's 7.50 minus 2X. So because we've calculated X, we can determine what the concentration of the NO has to be. It's 7.50 molar minus 2 multiplied by 3.629 with a guard digit molar. And because the 7.50 is only accurate 2 places past the decimal point, and this is a subtraction problem, your answer will only be accurate 2 places past the decimal point. And so the equilibrium molarity of NO turns out to be 0.24. Part B says, what is the percent dissociation of NO? So when you're doing percent dissociation, it's how much of the substance reacts away divided by its original amount multiplied by 100. So the amount that reacts away is what you see in the change line. And that's underneath the NO, it says 2X divided by the original amount of NO, which is the 7.50, and then you multiply by 100 to make it a percent. Because we know the value for X, the percent dissociation will be 2 minus the X value of 3.629 divided by 7.50, and then that fraction multiplied by 100 will give us a percent, and this comes out to 3 significant figures, 96.8%. Problem number 5. This is a problem not related to equilibrium, but it's a solution chemistry calculation, which will be relevant to things we're going to be doing in lab for the good part of the semester. A solution is prepared by dissolving 0.125 moles of calcium chloride in enough water to make 500.0 milliliters of solution. A, calculate the molarity of the calcium chloride in the solution. Molarity is defined as moles of solute divided by liters of solution. The solute's what's being dissolved. That's the calcium chloride. So it's 0.125 moles of calcium chloride divided by the volume of the solution in liters, which would be 0.5000 liters. 3 significant figure number divided by a 4 significant figure number. The answer will come out 3 significant figures, and this will give us 0.250 moles per liter or 0.250 molar in calcium chloride. That's how molarities are calculated. Now, part B is a demonstration of a technique we're going to be using quite a bit in lab, where we're going to be mixing substances together, causing their molarities to decrease because they're being diluted. Part B says we're going to take 100.0 milliliters of the calcium chloride solution, and we're going to mix it with 10.0 milliliters of water. So we're taking 100.0 milliliters of the calcium chloride solution we've just calculated its molarity for in part A, which is the 0.250 molar. We're going to add water to it. What's that going to do to the molarity? It's going to dilute it. It's like if you have a Coke at McDonald's and somebody walks up and pours a whole bunch of water in there, it's not going to taste as good because the sugar's been diluted. Anytime you mix something with water, you lower the concentration of the dissolved substance. So in this particular case, if we want to calculate what the new concentration of the calcium chloride is, its new molarity, this is the dilution calculation. And in Chem 1A, one way we learned how to do dilution calculations is with a dilution equation. MCVC equals MDVD. This says the molarity of your original concentrated solution multiplied by the volume of the original concentrated solution you use must equal the molarity of the newly created diluted solution multiplied by the volume of the newly created diluted solution. So to use this equation, we have to identify each of the variables. The concentrated ones on the left side, MC and VC, are relating to your original solution, which is the 0.250 molar calcium chloride solution. So we're using this as our concentrated solution. Now we made 500 milliliters of it, but we're not using 500 milliliters of it in part B. It says we're only taking a 100 milliliter sample of that. So the volume of the concentrated solution we're using is 100.0 milliliters. MD is going to be the molarity of the newly created diluted solution. That's what we don't know. We're going to solve for that. But what's going to be the volume of the newly created diluted solution? It says we take 100 milliliters of the original calcium chloride solution and mix it with 10 milliliters of water. That's going to make a total volume of 100 plus 10, 110 milliliters. So we now know 3 out of the 4 variables in the dilution equation. We just solve for the one variable we don't know, which is M sub D. So M sub D will equal MCVC over VD. Molarity of the original concentrated solution, 0.250 molar. We're using 100.0 milliliters of it, and the final volume is going to be 110.0 milliliters. The units of milliliters cancel out, and we're going to wind up having molarity as our final answer. And this should be the lower molarity of the newly created diluted solution, and it does come out lower than 0.250. It comes out 0.227 molar in calcium chloride. Question C represents one other concept you're going to have to understand when dealing with solution chemistry. It says calculate the molarities of the calcium ions and the chloride ions in this new solution. So the solution we've created is 0.227 molar in calcium chloride. Question C wants you to be able to tell me what the concentration of the calcium ions are and what the concentration of the chloride ions are. Calcium chloride is an ionic compound made up of a metal ion and a nonmetal ion, calcium and chloride. When ionic compounds dissolve in water, the metal ions separate from the nonmetal ions. So the calcium ions float off separately, they should have their own molarity. The chloride ions float off separately, they should have their own molarity. And the way you calculate them is actually really simple. If you look at the formula of the compound that's being dissolved, calcium chloride, it's CaCl2. There's 1 calcium ion in the formula. So every 1 calcium chloride formula unit that dissolves only gives you 1 calcium ion. If you had 227 calcium chlorides dissolving in water, that would give you 227 calcium ions. So essentially, all you have to do is take the molarity of the compound that's dissolved, 0.227 molar calcium chloride, multiplied by the number of ions in the formula for that particular species. There's 1 calcium in the formula, so I'm going to multiply 0.227 molar times 1, and that's going to tell me what the molarity of the calcium ions are going to wind up being in the solution. That comes out 0.227 molar. Now, if you understand that, then the second one should be doable. If there are 2 chloride ions in the formula of calcium chloride, Anytime you dissolve 1 calcium chloride in water, it's going to release 2 chloride ions. You're going to have twice as many. Its concentration will be twice as high. So once again, all you do is you take the molarity of the compound, 0.227, and multiply by the number of the particular ions in the formula. There are 2 chlorides in the formula, so we're going to multiply 0.227 molar by 2, and that means the solution will be 0.454 molar in chloride ions.